patterns. So let's take this topic now on patterns. We're going to start with an example. This is an example of a sequence. A sequence is defined as something with commas between them. So we look at this sequence here, and it's 2, 5, 8, 11, 14, and 17. And what we typically do is we write the numbers out again, 2, 5, 8, 11, 14, and we just draw a link between them. See, is there a common pattern? So we draw a loop between them. And we say, how do we get from 2 to 5? Well, we could get from 2 to 5 by adding 3. 5 to 8, adding 3. 8 to 11, adding 3. That looks pretty promising, I think, as a set of numbers. We could also get from 2 to 5 by multiplying it by 2.5. So we could either get here through multiplication or through addition. But if we multiplied that by 2.5, 2.5 times 5 would be about 12.5. And 2.5 times that would be 20. So it doesn't look like it's multiplication. It's addition, really. So we'll be able to see here that there's a common link between each term and the next. And if there is, we call that an arithmetic series. So this is one type of series. It's on your program, and we call it the arithmetic series. Now, let's look at the few observations about it. The first term is always called T1, term 1. That's just terminology. We're learning new letters or new symbols in this area of the course. It's also called the letter A. Handy enough, it's the first letter of the alphabet. So that's fine. And it's always T1 is A for any series. So we have that association there. There's a common difference here. Because 2 goes to 5 with 3, and 3, and 3, and 3, and 3, not so much that there's a difference, but there's a common difference. And the difference is additive. We call that D. And D is 3 everywhere. And because it's 3, or because it's a common difference, we can now say that this is now an arithmetic sequence. This defines it. An A and a D that's constant. Now, finding the sequence and series is the arithmetic because of 2. They give you formulae for this. And these are in the tables, and we can look them up. They tell you what the Tn is, the nth term. And they also tell you what the sum of the n terms would be. So basically what they say is they say that Tn, the formula says, is A plus n minus 1 times d. That's Tn. Now, n is the nth term. So T1 would be the first term. And anywhere you'd see n, you'd put in 1. 1 minus 1 would be A plus 1 minus 1 would be 0. It would be just A, because 0 times anything is just nothing. Let's look at the formula going forward and say if Tn is equal to A plus n minus 1 times d, T1 would be A plus 1 minus 1d, T2 would be A plus 2 minus 1d, T3 would be A plus 3 minus 1d, etc. That's 1 minus 1, that's 0. So if that's 0, it falls out. That's just A. 2 minus 1 is 1, so that would be A plus d. This would be 2, so A plus 2d. And really what they're saying is, if we look at the picture here, that the T1 is A, is 2. The second term is 2 plus 3 is 5. 2A plus d. The third term is A plus D plus D. 2 of them. And the fifth term, for example, will be you start on the 2, and then you go 1, 2, 3, 4. So T5 would be T or A plus 4D. Because you had 1 and you went 4 loops to get forward. Or T5 is T1 plus 4D. So in general, this formula, Tn, is equal to A plus n minus 1d, seems to make sense and seems to work. And that's a formula. It's there. It's in the tables. You don't have to remember it. You just use it. The next one then is Sn. And Sn is a different concept. Sn isn't the term, but the sum of the terms up to that point. So Sn is the sum up to date of everything to the left. So for example, if we were to look at this series now and say, if I just took one term here, that would be S1. Because what I have is I've got one term, and the sum to that point is just 2. So S1 is 2. But if I went for the first two terms, S2 would be 2 plus 5 is 7. And if I were to go further and do the whole series like this, and let's say I rewrite the numbers out, and I say 2, 5, 8, 11, 14, let's say I went for S5. S5 is all of the first 5 added together. So 2 plus 5 plus 8 plus 11 plus 14. That's 7 plus, 7 plus 8 is 15 plus 11 is 26. That's 40. So S5 is 40. Now, it would take us a while if we were adding up all the time. So maybe there's a formula for this, and there is. And the formula is given here. In the tables it's given. It's this one here. Sn is n over 2, 2a into, plus n minus 1d. So we'll write that out on this page here. Sn is equal to n over 2, 2a plus n minus 1 times d. Now, that looks like a lot of letters. But remember that a is T1, and that d is the common difference. So effectively, a in this case was 2 and d was 3, because our sequence was 2 plus 3 plus 3 plus 3. This was T1 equal to a. So now we have this equation that's not as complicated. And it just says that Sn is equal to n over 2. 2a would be 2 times 2, plus n minus 1 times d, which is 3. Continuing with this, n over 2 is n over 2 times 4, plus multiplying in the 3n minus 3. If I continue with that calculation, I get Sn is equal to, staying inside the brackets and sorting that out first, 3n plus 4 minus 3 would be plus 1. Sn is equal to n times 3n plus 1 over 2, or if we wanted, 3n squared plus n over 2, if we multiplied the n in. We still have an n in it, but that says that if I said S1, I could work it out. S2, I could work it out, and S5. So I invite you now to plug in the values for S1, 2, and 3 into that equation there. Okay, so let's continue with this now. So S1 would be 3 times 1 squared plus 1 over 2. 3 times 1 squared is 1. 1 squared is 1. That's 3 plus 1 over 2. And that's 4 over 2, which is 2. S2, 3, 2 squared plus 2 over 2. 2 squared is 4. That's 3 by 4 is 12. So that looks like 12 plus 2 over 2, 14 over 2. I'm getting 7 for that. And S5, 3n squared is 5 squared plus 5 over 2. 5 squared is 25. 3 times 25 is 75. 80 over 2, and that's 40. So it looks like I've got S1 is 2, S2 is 7, and S5 is 40. Now let's see if those numbers are actually correct. Let's see if we can find the original table. The original table, well, we rewrite it out. We just rewrite out the original table. It was, or sequence, I mean. It was 2, 5, 8, 11, and 14. This was T1, T2, T3, T4, and T5. S1 is T1 because you've only added up the first one. So S1 is T1 is 2. And that's what we got. We got that S1 was 2. Now S2 is 7. Well, S2, remember, is the first term plus the second term. That's its definition. And that's really 2 plus 5, because they're the first term and the second term. And 2 plus 5 is 7. We look at that and we say, yeah, that looks pretty okay. And now let's look at S5. S5, well, S5 is defined as T1 plus T2 plus T3 plus T4 plus T5. And that looks as if it's 2 plus 5 plus 8 plus 11 plus 14. That's 7, 15, 26, it's 40. And S5 is 40. Now, we could go on forever, but it's just proving the point that this formula here, Sn, is reliable, Tn is reliable, the two formulae work. So you can use them for anything. So just checking the formula in action then, in your notes, what's the value of the fourth term? Well, the Tn formula is given by the general version. T4, you just stick in 4 wherever there was an n, so you get this. T4 is 2 plus 4 minus 1 times 3. 2 plus 3 times 3. 2 plus 9 is 11. And if we look at the terms in our sequence, the fourth term is 11. The sum of the first 3 terms, Sn is all of this. Quite a lengthy formula. We're looking now for S3 to try it out. And we say it's 3 over 2, 2 times, well, A, we know the first number was 2. D, we know was 3. So we plug in all of this. And with this calculation, going through all the maths, breaking in the brackets in the standard BIMDAS way, we find that the answer we get for S3 with the formula is 15. Now, S3 here is the sum of the first 3 numbers, 2 plus 5 and 7, 2 and 5 and 8, 2 plus 5 is 7, 7 plus 8 is 15, S3 is 15, as we expected and predicted here and got here, so the formulae work. So that's arithmetic series and sequences, almost. The first term is T1, is S1 is A. S1 is T1, S2 is T1 plus T2, S3 is 3 that, Sn is all the way to Tn. You might, in a different part of your course, have considered that Tn this way, with the sigma, because it's the sum of all of them, if we were representing it like we might do in statistics. This relationship and association, though, I would suggest that if you've got a highlight marker or a red biro or something, that you highlight. This is really important because it's not in the book. It's not in the notes. Sorry, it'll be in your textbooks, of course, but it's not in the formula page. It's not in the formula book. And it's just a subtle way, and you will most likely have to use it. And it happens and it applies not only for arithmetic series, but for every conceivable series. And what it says is that the second term is the sum of the first two terms minus the sum of the first. Tn is Sn minus Sn minus 1. Let me just show that so that it's clear. T1, T2, T3, T4, T5. 2, 5, 8, 11, 14. It doesn't matter what the numbers are for this piece of work here. What we get is that S1 is T1. It's the sum of, which is 2. S2 is T1 plus T2, which is, I'm going to write this differently. It's the same question. I just want the layout to be a bit different, so bear with me. I'll do that again. T1, T2, T3, T4, T5. S1 is equal to T1, which is A. Sorry, which is 2. Let's call that 2 there. Get it right yet. It's just for the presentation, so you'll see it more visually this way. T1, T2, T3, T4, T5. 2, 5, 8, 11, 14. Okay. So S1 is defined as T1, and that's equal to 2. S2 is T1 plus T2, which is 2 plus 5. S3 is equal to T1 plus T2 plus T3, which is equal to 2 plus 5 plus 8. S4 is equal to T1 plus T2 plus T3 plus T4 equals 2 plus 5 plus 8 plus 11. Now, if we look at this particular picture here, what we're seeing is that what's the difference between this row here and this row here? Line 3 there and line 4. What's the difference? What's in this row that's not in this row? It's like you spot the difference. This is the only thing that's different, isn't it? So this one has a T4 and this one doesn't. Is that okay? So what you can say is that S3 is equal to T1 plus T2 plus T3, and S4 is equal to T1 plus T2 plus T3 plus T4. What is S4 minus S3? If I were to take this from this, what would I get? This minus this? I would get T1 plus T2 plus T3 plus T4 minus T1 plus T2 plus T3. These would all cancel. And I get S4 minus S3 is T4. Or T4 is equal to S4 minus S3. Or more generally, Tn is equal to Sn minus Sn minus 1. Effectively what we're saying is what we're saying is that Sn is equal to Tn minus Tn minus 1. So if I've got 2, 5, 8, 11, 14, etc., and I want to find this term here, T4, I can work out this total, S4, take away this total, S3, and get S4 minus S3 is T4. Is that okay? And we'll be using that calculation in a moment. Okay, so here's a question now. Given terms of a sequence, find the general formula. So here you've given numbers, and from that you're asked to find out what the formula is. So here you're told T1 is A, and D is 3. Find the general formula. Tn is equal to A plus n minus 1d. Plug in the numbers and tell me what formula you get for this particular sequence, the 2, 5, 8 one. What is it? So all we're saying is just plug in the numbers for A and for D there and get the equation. So finishing this, we say T1 is A is 2. So we say Tn is equal to A, which is 2, plus n minus 1 times 3. And if we wanted to solve that, we say, well, not solve it, if we wanted to make it a little tidier, if Tn is equal to 2 plus n minus 1 times 3, we'll multiply in. So Tn is equal to 2 plus 3n minus 3. Tn, grouping the things together, 3n, 2 minus 3 is minus 1. So that's our general term. And to prove it, T1 would be 3 times 1 minus 1, which would be 3 minus 1, which would be 2. T5 would be 3 times 5, minus 1, which would be 15 minus 1, which is 14. And if we look at our series, we can see it here, or our sequence. T1 is actually 2. And T4 is actually, T5 is actually 14. And that's what we got with the formula. So it's working. So it's not the general formula now. It's not the A plus n minus 1d. But we're saying this one is 3n minus 1. Okay? (3n), so we're asked there to get the common difference. We found it, and we found that the general expression for Tn, for the nth term, we wrote down the general from the tables. We found both A and D from our picture of our data, our 2 and our 3. We plugged in the numbers, and we got Tn is equal to 3n minus 1. That's a question that has been asked and can be asked. A question form that can be asked. They might say, what's the sum of the terms to a certain point? So again, you write down, well, there's a formula, you look it up, and there's Sn. You plug it in, but you know that A is 2 and that D is 3. So I leave you to plug in those numbers as well. Write down the Sn specifically for this sequence. So returning to this question now, A is 2 and D is 3 because we knew it was 2, 5 and 8. We knew this was a plus 3. So we just plug the numbers in. Wherever we see A, we plug in the number 2. And wherever we see D, we put in 3. Sn then 2 times 2 is 4. 3 into n minus 1 is 3n minus 3. We group them together. That's a real number. That's a real number. That's n's. So that's going to be 4 minus 3, which is 1. That's going to be 3n plus 1. And we get 3n squared plus n over 2. And that's our Sn. And we can try that. We don't have to. But we could say, let's try S2, just for testing it. S2 would be 2 squared plus 2 over 2. 2 squared is 4. 3 times 4 is 12. 12 plus 2 is 14. 14 divided by 2 would suggest it's 7. And the first two terms, 2 plus 5 is 7. So it works. Now, what I'm going to do now is I'm going to show you how many different ways the syllabus and the past papers can ask you exactly the same question. Remember that you know how to do the question now. If you know 2, 5, 8, if you know what the T1 is, what the A is of an arithmetic series sequence, and you know what the common difference is, if you know A and you know D, the question is over. You can use the formula and it's sorted. Is that okay? So how do they hide it? How do they make the pattern a little bit more obscure? So this is the first question. They say, you're told the first two terms and you're told it's arithmetic. That's all you're given. So you're told that T1 is A is 5 and T2 is 15. Can you work out the equations at this stage? What else are you also told? You're told it's arithmetic. What does that mean? That you get from the first term to the second term by adding. Is that okay? Or by doing some subtraction. It's addition or subtraction. So what's the link between 5 and 15? How do you get from 5 to 15? Plus 10. Not multiply by 3, but plus 10. Because you're told it's arithmetic. So if you're told that's plus 10, you know the next one is going to be 25, etc. But you also know that that's D. So really what you're saying is if A turned out to be 5 and D turned out to be 10, could you solve the equations? It's over, isn't it? Just the second way of asking for it. So you just work out what the common difference is. D is 10. And if you know A is 5, you know D is 10. It's the same question as the first one. Is that okay? So here you're told the first term and the common difference. And you're told it's arithmetic. So here you're told, actually, we're only going to give you T1 of A, of 5, and we're going to say that D is 10. How do we solve that one? If we're told that D is 10, can we get the second term, do you think? How do we get from the first term to the second term? We do the loop, don't we? We add in the 10, so this makes this a 15. Does it look like the same question as before? We have A, we have D, it's over. Now, this is slightly more slick. They say they give you any two terms and told it's arithmetic. Here they're saying, we're going to give you T1, and we're going to say that's 5. And T6 is 153. How do you figure out now what the series is and the sequence is? Can you figure it out now? Leave it with you for a minute, okay? Tell me what D is. Okay, give it a minute. Think about how you might relate T6 to T1. Or what does T6, how would you get to T6 from T1? What would you have to do? How would you figure it out? If you were to draw the thing in, how would it work? Okay, let's go with this. Well, you could say that T1 to T6, well, T2, T3, T4, and T5. If I was drawing the curtains, I'd say 1, 2, 3, 4, 5. I'd have to add 5 numbers to this 5 to get there. I'd have to add D here, 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 and here. Because T2 would be T1 plus D. T3 will be T1 plus D plus D. T4 will be T1 plus D plus D plus D. Or I could look up the formulae. And the formula says that Tn is equal to A plus n minus 1D. It would actually tell us that T6 is equal to A plus 6 minus 1D. Or that T6 is equal to A plus 5D. But A is T1, so T6 is equal to T1 plus 5D. Really what they're saying is that this number here, if that's T1, and this is T6, the difference between them is 5D. That plus that equals that. Because there's 1, 2, 3, 4, 5. Is that okay? So can I solve that? Well, I should be able to. It says that 5 plus 5D is 153. How do I solve that? I don't like the 5 on this side, so I say 5 plus 5D equals 153. I take 5 from both sides. They cancel. So I get 5D is equal to 153 minus 5, which is 148 or something, is it? And then I work out what the D is from that. Is that okay? Happy with that? Now I'm going to ask you to do a question, and it's this. Given any two terms and told it's arithmetic, T1 is equal to A is equal to 5 and T6 is equal to 15. Find D. Okay, over to you. So you're given two terms and told they're arithmetic. The first one is A is 5, and the sixth one is 15. So here we go, and we say T6 is 5 terms away. 5 common differences, 5 to 15 is 10. And 5 differences, 5D here is 10, D is just 2. And does that make sense? Well, if we were to look at it, we'd say 5 is here, 2, 3, 4, 5. Let's add 2 all the time, plus 2, plus 2, plus 2, plus 2, and plus 2. We end up with 7, 9, 11, 13, and back to our 15. This is T1, that's T6. So T1 was 5, T6 was 15. We found D as 15 minus 5 divided by 5, because there were 5 D's in the gap. So really, all we're saying there is you could be asked or given in the exam, not the first and the second term, but any 2 terms. And if you're told it's arithmetic, you can still solve it. So that's the workings. Tn or T6, you'd work it out. T1 is that. T6 minus T1, you get 5D is 10, D is 2. Next question. Given an expression for Tn, find the individual terms. Tn is 4n minus 3. Find T1, T2, and T3. So you're told that Tn is equal to 4n minus 3. So find T1, T2, and T3. Over to you. Just on a small note, you've been really, really good. I mean, you're tremendous. I've always been hugely impressed with the students I meet from Dublin, Cork, and Limerick. If you do have to nip out, and it does happen, out that door if you're on this side, or out that door if you're on this side. Try not to cut across this line here, because Mus has taken the film. Now, I know that somebody passed there this morning, and it was no problem because Max spotted it, and he just moved to the cameras and stuff like that onto my notes, so there wasn't a problem. But it's just a problem for Max that he's got to figure out if there's any traffic or something like that. You know? Also, too, that, you know, people would have seen people yesterday leave in the last session at 5 o'clock and 5:15 and stuff like that. I'd absolutely no problem with that. I fully understood that people have commitments, they're being collected, and they've other things. People are coming in from sports matches and all that sort of stuff like that. And the way you walked out was fabulous, it was very respectful and all that. So I have no problem, and I'm not upset. If you've got a commitment, don't be saying, I told him be 5, when will he finish, and all that sort of stuff. But everybody has done it very quietly and very respectfully, and you're here for when you're here to be here, you know what I mean? So I'm using your time there on that. So just this particular line here, because Mus is being annoyed now with me, you know? But this will all be cut out of it. Is that okay? Well, it better be, okay? Yesterday was more difficult because that door was locked and we hadn't sorted that out. Okay, T1 then, what did you get? You got 4 times 1 minus 3, which is 4 minus 3, which is 1. T2 is 4 times 2 minus 3. 4 times 2 is 8, minus 3 is 5. T3 is 4 times 3 minus 3, which is 12, minus 3, which is 9. Now, sometimes it's really, really useful when they give you the formula for the numbers here to actually plug in the first 2 or 3 terms. Because when you write them out again and you say 1, 5, 9, T1, T2, T3, it sort of becomes so clear to you what that series is. You fully now see it. And it's probably worth it for that. You know you're not going to make a mistake. You know it's arithmetic. You know we do all the calculations. You know you do all the S's and all that stuff on it. So there's the expression. We plugged in T1, T2, and T3, and we got the values 1, 5, and 9. we can now do other information exactly as before. This is a popular twist that comes up. It's in the syllabus specified. And it said, given an equation for the general term Tn is equal to 4n minus 3, find the number of terms in the sequence with values below 200. So basically what you're saying is, if I had 1, 5, 9, presumably 13, etc., going forward, we can write in a few of them. 1, 5, 9, 13, 17, 21, all the time conscious that I'm adding the 4, plus 4, plus 4, plus 4. The question asked is, how many of these do you get up to the point 200? You're saying, I don't really want to do this in the exam. It's just too much time. It's just a mess. I don't have the time for this. And what happens if they said 2,000 anyway? And I could easily get it wrong and all that. So what they say is, well, what term actually is 200? The general formula is Tn, in this case, is 4n minus 3. How would you find out the nth term that makes that nearly 200? Well, this is the value you get. It gave us 1, 5, 9. And by the way, will the sequence ever reach 200? Will 200 be one of the numbers on it? Do you think? Will it be? Well, look at all the numbers. Anything about the numbers? 1, 5, 9. Anything about them? They're all odd. They're right? If they're all odd, will 200 be one of the numbers? No. Is that okay? That be fair? It's going to be an odd number. But which term is it? Well, what we do is we just guess. And we say not guess. We say 4n, let's make 4n minus 3 equal to 200. Solve that equation. Tell me what n is. And then get the t that associates with that. Okay, 4n minus 3 is 200. 4n equals 200 plus 3, taking the 3 over. 4n is 203. Therefore, n is 50.75 or something like that. But we've never had a term anything other than an integer. So 50.75 makes no sense. Now, do we truncate? Do we round? It really doesn't matter. I'm going to truncate, really. I'm going to say that's 50. If it turns out to be 51, I'll get it right at the end. So basically what my guess is that it's around the 50th term that this is going to take hold. So the general formula was Tn is equal to 4n minus 3. What's t of 50? T of 50 is 4 times 50 minus 3. That'll be 200 minus 3, which is 197. If we had tried T51, we'd say 4 times 51 minus 3. That'll be 204 minus 3, which would be 201. What this is really saying is that term 50, term 49, all the way back to term 1, and term 51, that the numbers at this stage for 50, 197, and this is 201. My guess is that this is going to be 193 because everything is linked by the plus 4. Now, how many terms in this sequence actually have values less than 200? Is the 50th term less than 200? Okay? So the answer is 50 terms. So even if we had rounded that up to 51, we would have got T51. We would have seen that that was 201, and we would have said, well, that can't be included. It was the one before it. Is that okay? But all we did was we just took the equation Tn, and we made it equal to whatever limit they were looking for. They might have wanted all those under 20 or under 50 or under 1,000 or whatever. And that's how we do that. So what's left in there? So there we go. There's our T50, 197, our T51, 201. So clearly there are only 50 terms. We don't go to the 50 first. Now, this is the question that I said is not in the formula tables in terms of the associations between S's and T's, but it's just that common understanding that we picked up earlier. Given an expression for Sn, not Tn, Sn, for the individual terms where Sn is equal to that, find an expression for Tn. Okay, so what they're saying is, I'm not going to tell you about these things individually, but I'm going to tell you about them collectively. So Sn is equal to n squared. How can I get Tn? Well, what I could do is I could write down S1, S2, and S3, S4. In fact, it would be much better if you did. So S1, S2, S3, and S4. So write down the values for those, please. Okay, we're going to do this. Sn, S1 is 1 squared is 1. S2, 2 squared is 4. S3, 3 squared is 9. And S4, 4 squared is 16. But remember, S1 is the sum up to the first term. So if we were to write these terms out, T1, T2, T3, T4, S1 is the first term, so that's a 1. S2 is the sum of the first two terms. So we know that 1 plus something is going to be equal to 4. What do you reckon that something is? 1 plus what is 4? Might be 3, would it? Is that okay? So really what we're saying, though, is S2, that T1 plus T2 is 4. But T1 we know is 1. Therefore, T2 is 3. We take S3. What's S3? Well, S3 is all of this for the first three terms. And that we know is 9. So T1 plus T2 plus T3 is 9. But really, T1 plus T2 we know is 4. So 4 plus t3 must be 9. t3 must be 5. And then we say, well, what's S4? 16. All of this is 16. But S4 is T1 plus T2 plus T3 plus T4. But what is it really? Only T1 plus T2 plus T3, S3 plus T4. S3 we know is 9. So 9 plus T4 gives us 16. What's T4? 9 plus what gives us 16? T4 is 7. This becomes 7. So now if we were to look at the series or sequence, we'd see it's T1, T2, T3, T4 of 1, 3, 5, and 7. 1, 3, 5, and 7. Does that look like a reasonably familiar arithmetic series sequence for us? Starting with a number, adding the same thing all the time, we have Tn. Tn in general is given as a plus n minus 1d. A we know is 1, and d we know is 2. So Tn would be a, which is 1, plus n minus 1 times 2. Tn would be 1 plus 2n minus 2. That would be 2n minus 1. So we certainly could solve it. That's one way of doing it. So we look at the notes and we say that's certainly one way of doing it. 2n minus 1 seems to be our, and is that right? Tn is 2n minus 1. T1 would be 2 times 1 minus 1, which is 2 minus 1, which is 1. T4 is equal to 2 times 4 minus 1, which is 8 minus 1, which is 7. T1 is 1. T4 is 7. Yeah, it looks like it's all right. These are all working out. That equation is right. It is 2n minus 1. Now, was there another way of doing that? Well, let's go back to what they asked us to do. They said, give us an expression for Sn, find the value for Tn. Well, one way of doing this is that T1 is S1. T2 is the sum up to the first two terms, take away the sum up to the first term. And Tn is the sum of all the terms up to n minus the sum of the terms up to the one before it. So effectively, that is the killer equation. That Tn is equal to Sn minus 1. That equation is not given in the tables, okay? But it's a lovely association. Now, what they're saying is that if you know that Sn is equal to n squared, could we work out the Tn? Well, we can. We can say that Tn is equal to Sn. Well, Sn is n squared. Minus Sn minus 1. Well, what they're saying is that everywhere you had n before, you now put in n minus 1. So you say n minus 1 squared. N squared minus, we multiplied this out, n minus 1 times n minus 1. N squared minus the FOIL method. N by n is n squared minus n, minus by minus is plus, and brackets around the whole lot. That's n squared minus, within the brackets, n squared minus 2n plus 1. And now we distribute the minus into the brackets because we've sort of grouped all those things together. We get n squared minus n squared plus 2n minus 1. These two things cancel, and we get 2n minus 1 for Tn. And that shouldn't surprise us because when we did it the other way, we got 2n minus 1, 2n minus 1, 2n minus 1. So if you look at the notes there, we took the general term for Sn, and just as we would say when S1 we just take the value of 1 and stick it in everywhere there's n. We say 1 squared. S5 would be 5 squared. So Sn minus 1 will be n minus 1 squared. We just take the number and plug it in. We expand it out, work the whole thing out, and we get Tn is equal to 2n minus 1. We checked other values then for the Tn. We got 1, 3, 5. So 1, 3, 5. We do our d. We can work the whole lot out, etc. And there's our sums to the first three. Now, this is the last question on the arithmetic series. I just want to do one later on the quadratic. But this is a very interesting point here. There's a key word in this question, and it's the word prove. You're asked in this question to prove that a series or a sequence is arithmetic. That's just not good enough to say, it is, or it holds a bit. No, it's true all the time. So I'm going to give you the series or the sequence, and I'm going to say it's 1, 5, 9. So we start off here and we say we want to prove that there's a common difference always. 1, 5, 9, 13, 17, 21. Now, when we look at this, we see that that's 4, that's 4, that's 4, that's 4, that's 4. But will it go on forever? It will, yeah. But how do you know? I just do. No, how do you know? That's not good enough. To prove something, you have to prove that it's always true. Well, I can't do every number. Well, then how do you prove it? Prove it means that it applies for Tn, for the general case Tn. So what we're asked to do now is that we've got to figure out how we can prove that a series or a sequence is arithmetic. Well, what's the definition of a series that's arithmetic? Basically, the definition is that if you go from any term to the next one, you add d. Any term to the next one, you add d. So basically it's saying is that for any term tn minus 1, if you go to tn, you add plus 4. That's what we've got to prove. Or actually, that it's even, we have to prove that there's a common difference. Doesn't matter what the number is. As long as it doesn't change, as long as the difference between one term and the next one is always a constant, you've proven that. So let's just see if we can do that. What we do here is we say, okay, we want to prove that in general, that Tn and Tn minus 1 are separated by a common difference. So here's the equation. We've got 1, 5, 9, 13, 17, 21. Find the general equation for that. Over to you. Write down the Tn in general for that equation. Okay, we have our numbers. So the first thing you have to remember is that T1 is A, and that whatever links 1 to 5, if that's plus 4, and it's always the same, that's D. So A is 1 and D is 4. We look up the tables, the formula tables, and it tells us that this one is A plus n minus 1D. That's the general formula. But our specific one is that Tn is equal to A, which is, that's 1. We plug in the numbers, plus n minus 1 times, D is 4. So in this particular equation, we get Tn is equal to 1 plus, and multiplying in 4n minus 4. Distributing the numbers across, Tn is equal to 4n minus 3. So that's our formula for this series. So Tn is equal to 4n minus 3. What's Tn minus 1? Well, what we do here is we just plug in n minus 1 wherever there's n. So we say 4 into n minus 1 minus 3. And that becomes 4n minus 4 minus 3, which is 4n minus 7. So really what we're saying is that in the general case, that when we're looking at Tn up here, and that's 4n minus 3, the one beside it, Tn minus 1, is 4n minus 7. And actually, that's not surprising, because if you add 4 to minus 7, you get minus 3. But what's the common difference? The common difference is defined as Tn minus 1, because that minus that is 4. That plus 4 is that minus 4 is that minus that is 4. So we say D is equal to Tn, which is 4n minus 3, minus 4n minus 7. That's 4n minus 3, putting in the minus 4n plus 7. That's equal to, the two 4n's cancel. We get minus 3 plus 7 is 4. D is 4. What we're really saying there is that that's very significant. That the difference in this equation here, D is 4. Not that the 4 is important. That's not the matter. The matter is that there's no n in there. There's no variables. That's saying that the difference is always a constant. If the difference is always a constant, you have proved. The proving is over. You pick up your marks. You've shown that for every single case, you took the general Tn minus 1, you've proven it, because there's no n in there. It's constant. It's true. So there we have calculating Tn minus 1, or Tn, 1 minus the other, 4n minus 3, Tn is 4. As the difference between Tn and Tn minus 1 is a constant, not dependent on n, it represents a common difference, D. Therefore, the sequence has been proven to be arithmetic. So here's algebra now coming in. And they say, solve algebraic expressions based on consecutive terms in a sequence. And they're going to give you 3 consecutive terms in the sequence. T1, T2, and T3. Or it may not be T1, 2, 3. It could be T, whatever, n plus 1, n plus 2, n plus 3. All it said is there are 3 consecutive terms. So let's imagine that they are Tn minus 1, Tn, and Tn plus 1. And they said the terms are k minus 1, 2k, and 4k minus 2. Solve for k. Now, if you read the note there, there's one really important term. It says, an arithmetic sequence has the following 3 terms. In fact, the first 3 terms, it's fine. So it's an arithmetic series. What do we know about it if it's arithmetic? By definition. How do we get from one to the other? We add a difference. Is that okay? But do we add the same difference here? Yes. So just take time out for a second here, back to mathematics. If somebody said you had 2, 6, and 4, you'd say 2 plus 4 is 6. You might also say 6 minus 4 is 2. But you could also say 6 minus 2 is 4. So in that tiny representation there, we have 3 different equations. So if somebody says to you then that you have t1 or tn and tn minus 1, and you've got, say, d, you could say tn minus 1 plus d gives us tn, because I'm thinking forward. If I was thinking backwards, I'd say tn, take away the d, and I'd be on the one below. Or if I was thinking a bit laterally, tn minus the one before it is the difference. Is that okay? So that's the way this thing works. So what they've done in the algebra here is just like the maths. They've said that these 3 terms are related. But the only thing we know for sure is that this d is the same as this d. So I'm going to write an equation for the first d. I'm going to call that d1 and d2. What's d1? Well, d1 is that plus d1 gives us this. But I could say d1 is 2k minus, d1 is equal to tn minus tn minus 1. Basically, that minus that. Or I could say d1 is equal to, in blue, I could say it's 2k minus k minus 1. Is that okay? Now, what's d2? Well, d2, this is this area here. That's what's going on over here. These 3 are, it's like 2, 4, and 6. It's like addition. That's a plus, by the way. That plus that is that. So what's d2? Well, 2k plus d2 is that. So I could do that. I could say 2k plus d2 is 4k minus 2. Therefore, d2 must be 4k minus 2 minus 2k. I could do it that way. Or if I wanted to do it with the letters, I could say d2 is tn plus 1 minus tn. And I could solve that again. Is that okay? So d2 is equal to tn plus 1 minus tn. Or d2 is equal to, in blue, 4k minus 2 minus 2k. But what do we know about d1 and d2? What do we know for sure? Isn't the sequence arithmetic? So mustn't this be a common difference? Yep. So d1 is d2. So if d1 is equal to 2k minus k minus 1, and d2 is equal to 4k minus 2 minus 2k, and d1 is equal to d2, solve for k. So now try that one. Simplify this equation, make them equal, and solve for k. Okay, so returning to that, 2k, spreading the minus in, is 2k minus k plus 1, minus by minus. 2k minus k is k plus 1. Here we get 4k minus 2 minus 2k. 4k minus 2k is 2k minus 2. So putting the two together, we get that k plus 1 is equal to 2k minus 2. We could take k from this side, or we could take the k's over, whatever we wish. We could say, take the two k's over. We said k minus 2k plus 1 is minus 2. Minus k is equal to, taking the 1 over, minus 2 minus 1. Minus k is minus 3. K is equal to 3. We've actually solved for k. Now, if that's right, let's go back to the original sequence, and it said it was k minus 1. So if k was 3, k minus 1 would be 3 minus 1 would be 2. 2k would be 6. And 4k would be 12. Minus 2 would be 10. So 2, 6, and 10. Does that look to you like an arithmetic sequence? 2 plus what gives you 6? 4. 6 plus what gives you 10? 4. Common difference. Solved. Okay? So now for the very last, there's the mathematics on it, solving for k. K is 3. Now, the very last topic in this patterns is that they give you a picture. They ask you to count tiles, or they ask you to look at a particular pattern. And they show you 1, 2, 3, or maybe 4 versions of it. And you get a series of numbers. And really all you're doing is counting them. And the numbers could turn out to be 2, 4, 6, 8, in which case you can do it. Or it might be 1, 3, 5, 7, in which you can do it. But it might be something slightly more awkward. It might be something like this: 1, 4, 9, 16, 25. In other words, when you go for the gaps between them, you might find that the first gap is 3, the second gap is 5, the next one is 7, and the next one is 9. And you say, oh, this is tricky. But then you go again, and you say, what would happen if I did it twice? And that would be 2, 2, 2. So if it takes 2 goes to actually figure out what the pattern is, to get it down to a constant difference, it's called quadratic. And quadratic patterns are on your program. So all we've done is we've counted the tiles. So that's the issue. But we've got these set of numbers. So let's look at how we deal with this 1, 4, 9, 16, 25. 1, 4, 9, 16, and 25. What we're saying is that when you've written out the numbers for the patterns in the question, whatever it is, tiles or marbles or whatever, golf balls or whatever they ask you to count or look at, that's just counting. You find that you get 3, 5, 7, 9, and you go again and you find it's 2, 2, 2. You now know it's quadratic. This is the way it's done. The term in quadratic is an squared plus bn plus c. You've seen that before for the good old minus b. That's your general term. There's going to be a term in n squared, a term in b, in n, and a term in c. So there's going to be an n squared, an n, and a c. But it works out very neatly. What you do is you go to the very bottom line here, the plus at the end. And A is equal to this second line, divided by 2. So whatever this number turns out to be, if that's 2, A is 1. If that's 4, A is 2. If that's 46, it's 23. So actually what we're getting is that Tn is now equal to 1. In this situation, 1 n squared plus bn plus c. Now we're still not there. Because actually what we have is we have to solve this thing, which is not great, but it's getting better. So we have a formula that says Tn is equal to n squared plus Bn plus C. But what we do is we just plug in numbers. We say, what's T1 and what's T2 equal to? We don't have to pick T1 and T2, we can pick other ones. But T1 would be 1 squared plus B times 1 plus C. T2 would be 2 squared plus B times 2 plus C. Now we could simplify that by saying that's 1 plus B plus C. That's 4 plus 2B plus C. But why are we doing this? We're doing this because we were told what T1 was. We're not trying to find them. We actually know them. T1 is 1. And T2 is 4. So what we have now are two equations. Equation 1, which says that 1 plus B plus C is 1. And equation 2 that says that 4 plus 2B plus C is 4. I think we could simplify those. We could take the first one and maybe 1 plus B plus C is 1. B plus C is 0. We could take the second one and we could say 4 plus 2B plus C is 4. 2B plus C is 0. Now we've got two equations that both hold, and if they both hold at the same time, well, they're called simultaneous equations. So at this stage we have B plus C is 0 and 2B plus C is 0. Simultaneous equations. So we just take one from the other and we find that minus B is 0. B is 0. Now if B is 0 and B plus C is 0, 0 plus C is 0. C is 0. So it's a very boring equation we got. We got an squared plus bn plus c is, well, what do we get? We got for a, we got 1. 1n squared plus no n plus no 0. We just got n squared. So effectively what the quadratic was telling us was that the nth term was actually n squared. T1 was 1, T2 was 4, T3 was 9, and T4 was 16. Exactly the particular sequence we were working from in the beginning. So that's how we solve it, that's how we do it, and we get our T that way. So we're now going to just do another straight example like that. Just leave it with you for a moment or two, and you might try the following numbers to see if we got a pattern question like this in the exam. They asked you to count tiles or pictures or pictograms or pixels or whatever. And the numbers they give you are as follows: 5, 15, 31, and 53. So they're the first four terms. And you've been asked to reduce that to the an squared plus bn plus c and see if you can do that. So you get your loops. If they don't fit, you go again, you bring it down to stabilization, and you see where you go. So give that a go. So the first difference, 5 to 15 is 10. 15 to 31 is 16. 31 to 53 is 22. And they're not the same. So we better go again. That's plus 6, and that's plus 6. So this is encouraging. In 2 goes, we actually got there. Not the first row, as sometimes, so it's not straight arithmetic, but the second one. It's quadratic. Now, we were told that if this number was whatever it was, all we had to do was divide by 2 to find out the a value. So if this number is 6, 2a is 6, a is 3. So effectively, we're a bit of the way there. We're saying that the Tn is equal to 3n squared plus bn plus c. And we now have to use the data here for the various t values. We can pick any one of them or 2 of them we like to solve this. But we have some values to get there because we need to solve this b and the c. So if we have 2 unknowns, we must actually have 2 equations. You can't solve 2 unknowns with 1 equation. So I'm going to take t1. t1 was 5, so 3n squared plus bn plus c would be the normal case for tn. So let's just try t1 then. t1 would be 3 times 1 squared plus b times 1 plus c. And that would be 1 squared is 1, so that's 3. So that's 3 plus b times 1 is b plus c, and that's t1. t2 is 2 squared plus b times 2 plus c. 2 squared is 4. 3 times 4 is 12. So that's 12 plus 2b plus c. But we know the values of t1 and t2. So that's equal to t1. That's equal to t2. And that's also further equal to 5 and 15. So effectively what we have now are 2 equations. Equation 1, we've got 3 plus b plus c equals 5. We can simplify that by taking the 3 across and say b plus c is 5 minus 3, or 2. That's equation 1. The second equation is this. We're going to get 12 plus 2b plus c is 15. Then we're going to take the 15 over. We get 2b plus c is 15 minus 12 is 3. Now we've got 2 simultaneous equations, as we had before, but we'll see what numbers they come out with. b plus c is 2, and 2b plus c is 3. Okay. So, as we would with ordinary straightforward algebra, b plus c is 2, 2b plus c is 3. We don't have to do anything with these equations because the c values are already the same. So we just take the first one from the second one. They cancel. And we get minus b is 2 minus 3 is minus 1. B is 1. So that's the first answer we have. B is 1. Well, if b is 1, we go to the first equation and we say b plus c is 2. 1 plus c is 2. C is equal to 2 minus 1. C is equal to 1. We've got c is 1. Does that work for the second equation? Well, 2 times checking. 2 times 1 plus 1 is 3. 2 plus 1 is 3. It's correct. So b is 1, c is 1. And if we go back slightly, we found that a was 3. So now we have a little table that we could put aside. And we could say, okay, a is 3. We've got that too. T1, T2, T3, and T4 was 5, 15, 31, and 53. We were using this equation here, an squared plus bn plus c, and the tn was equal to all of this. But let's plug in the values now. Tn is equal to an squared plus bn plus c. But let's look at our tables. Well, a is 3. That's tn is therefore 3. It's 3n squared plus b plus n plus c. That's 1 as well. So that looks like our proposed tn. our formula for Tn. Well, let's see, does that make sense? Let's try T1. T1 would be, plugging in the numbers, 3 times 1 squared plus 1 plus 1, which would be 3 plus 1 plus 1 is 5. T2 is 3 times 2 squared plus n, which is 2, plus 1. So 3 times 2 squared is 4. 3 times 4 is 12, plus 2 plus 1. That's 15. T times 3 is 3 times 3 squared, plus 3 plus 1. That's 3 by 3 is 9, 3 put 27. 27 plus 3 plus 1 is 31. And T4 is equal to 3 times 4 squared, plus 4 plus 1. 4 squared is 16. 3 times 16 is 48. Plus 4 plus 1 is 53. So we're getting here 5, 15, 31, and 53. And here we have 5, 15, 31, and 53. So we have reliably reduced this set of numbers in our pattern of golf balls or tiles or whatever we're counting through the 2 steps, and we have reduced them to find the A, B, and the 2 steps here brought us down to find the A value. The A value then, we worked on that, and we plugged in, and we used the simultaneous equations, knowing that the A was 3, to get the B values for 2 of these, and we got the B, and we eventually got the B and the C of 1 and 1. We got this equation here with just a 1 here and a 1, so 3n squared plus 1n plus 1. That was the B and the C and the A all known. We plugged in the values and we get 5, 15, 31, and 53 for the sequence that was 5, 15. I don't know how I managed to do that. I had it here, I think. For the sequence that was 5, 15, 31, and 53, we end up with 5, 15, 31, and 53. So that's that series done. So that's the end of the series on patterns.